Hello everyone, welcome to Engineering Explained channel. In this session, I am going to take other types of work transfer in thermodynamics. In the previous sessions, I have taken the definition of the work according to mechanics and definition of work according to thermodynamics, and later I have taken the PDV work transfer, which is very important in the most of the thermodynamic processes. And here I am going to take other than the PDV work, what are the different types of the work transfer are there. Here, this is the basic thermodynamics module 1, lecture 11 that contains electrical work, shaft work, paddle wheel work or stirring work, flow work, work done in stretching a wire, work done in changing the area of a surface film, magnetization of a paramagnetic solid. Here, there are forms of work other than PDV or displacement work. The following are the additional types of work transfer which may be involved in the system surroundings interactions. First one, electrical work. When a current flows through a resistor, when a current is flowing through a resistor, which is a resistor transfer of the electricity taken as a system, and there the heat it will generate, then there is a work done on it. Okay, in the resistor. And how that we have to take, there is electrical work. And how is the electrical work that we can decide even though there is no movement here. There is a work transfer into the system. I hear the system boundary of this to the register and where the electricity is entering, therefore work done on the system. This is because current can drive a motor, the motor can drive a pulley, and the pulley can raise a weight. And this is the work transfer. Because if this electricity, if you connect to the motor, it can drive the motor. And motor, if you connect it to the pulley, it can rotate the pulley. Then if you connect the pulley with the rope and weight, it can raise a weight. Then according to the thermodynamics, we can say it is a work done, and that is the electrical work. And here the parameters concerned to this electrical work we'll discuss. The current now I is the current in amperes is given by I equal to dc by d tau, the change in the charge to the change in the time, where c is the charge in coulombs and tau is time in seconds. If dc is the charge crossing a boundary during a time derivative. For this small amount of the time, dc, the small amount of a charge is crossing the system boundary. If E is the voltage potential, during that transfer of the energy, there is a voltage potential to driving force for this the flow of the electricity. Then the work done is given by dw is equal to voltage potential multiplied with a that charge, the charge crossing the boundary. Then this charge we can take from this equation dc equal to I into d tau. Therefore dc can be substituted as I into d tau, E into I into d tau. Then work done W can be given as integration of this equation 1 to 2 EI into d tau. Okay, this is a small amount of work done, and total work done can be taken as the integration of 1 to 2 EI d tau. Then electrical, this is the work done equation, and the electrical power is given by, okay, the rate at which the work is done. That is W is equal to power limit of d tau tends to 0 dw by d tau into E is equal to EI. The EI, this is the electrical power. This is rate at which work is transferred, that is the power. The next one is the shaft work. When the shaft is rotating, then how the work transfer is taking place. When a shaft taken as the system is rotated by a motor, okay, this shaft which is rotated by this motor is taken as the system. There is work transfer into the system. There is a work transfer into the system. Okay, then this is because the shaft can rotate a pulley. The shaft can rotate a pulley which can raise a weight. If you connect this shaft to a pulley, then pulley can raise a weight, and that's why there is a work done by the shaft. If T is the torque applied to the shaft, the torque, the twisting moment during its rotation, the torque applied by to the shaft, and d theta is the angular displacement of the shaft, then shaft work is this angular displacement for which the shaft rotates. That is angular displacement. Then the shaft work is given by W is equal to 1 to 2 T into d theta, torque multiplied with the angular displacement. Then, and the shaft power, a rate of doing work, that we can write W dash is equal to 1 to 2 T into d theta by d tau, that can be written as d omega. That is angular velocity is taken, where W is the angular velocity and T is the considered as a constant. See, pedal wheel work or stirring work. Here, this stirring of the fluid is taking place. If the pedal wheel, this one, if rotates inside the fluid, then the work will be transferred from this pedal wheel to the that fluid, and that is pedal wheel work or a stirring of the fluid. That work we have to take. As the weight is lowered and pedal wheel turns. As the weight is lowered here, then this pedal wheel turns. There is work transfer into the fluid which gets stirred. There is a work transfer into the fluid. There is a work transfer into the fluid which is gets stirred. Since the volume of the system remains constant, then the PdV is equal to 0. If the volume remains constant, the PdV work equal to 0. Already we have discussed this. The constant volume process, the work transfer is 0. Then if m is the mass of the weight lowered through a distance dz, okay, this is m is the mass of the this weight to be lowered through a distance dz. For a small distance dz, it will be lowered, and T is the torque transmitted by the shaft. Okay, here the shaft, for that there is a torque transmitted. This T is torque transmitted by the shaft in rotating through an angle d theta. The d theta is the angular displacement. And here what the shaft work in the previously we have taken, the same amount of work will be done here. And here the another work is done by lowering the work. Both are equated. The differential work transferred to the fluid is given by, that is dw is equal to, that is a small amount of work done is equal to mg dz, the mass acceleration due to gravity, dz is a small amount, for that weight is lowered, and t is the torque transmitted to the shaft, d theta is the angle of the rotation, and the total work transfer is written as W is equal to 1 to 2 this mg dz, that is equal to 1 to 2 W dz. Okay, that is because mg can be written as the weight. The mass into acceleration due to gravity is taken as the weight of the is to be lowered. Then that is equal to 1 to 2 T into d theta. Both are equated. Both are equated. This work, what is done during the lowering of the weight, is equal to the what is the work transferred by the rotation of the pedal wheel. Both are equated. And where W is the weight lowered. And this W, what is there? This is the weight is lowered. Then next one, D, flow work. The flow work significant only in the flow process or an open system, represents the energy transferred across the system boundary as the result of energy imparted to the fluid by a pump, blower or compressor to make the fluid flow across the control volume. And this flow work, when we will consider when the fluid is crossing the boundary. Systems like a pump, blower or compressor, there some quantity of the fluid is entering into the system and certain quantity of the fluid is leaving from the system. There we are going to consider the flow work. And this flow work is analogous to the displacement work, the PdV work. Similar to it is there. For that, let P be the fluid pressure in the plane of imaginary piston. Okay, their imaginary piston we are going to consider. We'll take in the next slide that imaginary piston, what it is, which acts in a direction normal to it. The work done on this imaginary piston by the external pressure as the piston moves forward is given by dw is equal to pdv, that is equivalent of the pdv work. And here we are going to take the system, the open system, or the system for which flow work is to be determined, right? Where the certain quantity of the fluid is entering into the system, certain quantity will be leaving from the system. The compressor, pump, blower, or a turbine, where the fluid will enters and leaves, and during that the certain work it does. And there the work done we are going to find out. Where dV is the volume of the fluid element about to enter the system. And here imaginary piston we are going to consider, and where the fluid pressure P is taken on the piston area it is acting, therefore dV is the, that is volume of the fluid element about to enter to the system. And dW flow can be given as pressure multiplied with the volume and dm, the change in the mass, and where dV is written as VDM. Therefore if you substitute dV equal to VDM equal to dV, then we can write there is a flow work at inlet can be written as dW flow in equal to P1 V1 dm. Okay, then the PdV there, the VDM we have taken, then the VDM at the inlet it is a V1 dm on. Similarly, flow work of the fluid element leaving the system is dW flow out can be written as P2 V2 dm2. Then the flow work per unit mass is thus W is equal to PV. Okay, the pressure into that volume. Okay, the total volume will be there for the inlet and the outlet we are going to take. It is the displacement work done at the moving system boundary. Okay, this is the displacement work. It is similar to the PDV work. Then work done in stretching a wire. When a wire is stretched, it stretches for a certain distance, length. Then if you leave it and comes to the original position. But on when we stretch it, there is a force is applied. Therefore, work is done on that system. And what is the work done during the stretching up the wire we have to take? Let us consider a wire as the system. If the length of the wire in which there is a tension tau is changed from length L to the L plus TL, the infinite small amount of work that is done equal to. Okay, here very small amount of work done during the stretching of the wire, infinite small amount of work. That is a very small amount of the work when in length is from the L to the L plus DL. DL amount of length will be extended. Then work done can be given as dW is equal to minus tau into DL, where this is the tension in the wire and dl is the change in length. The minus sign is used because a positive value of dl means expansion of the wire for which work must be done on the wire. Okay, on the wire the work is done. Therefore, that is a work done on the system we are going to take as a negative. Therefore, there is a negative work. For finite change of length, finite the particular length change, for that the work done can be given as W is equal to minus 1 to 2 FDL. Okay, there where limit the problem to within the elastic limit. This problem if you limit within the elastic limit, that means if, the elastic limit means when it is expands, it when we leave the force, it will regain its original position. That is the elastic limit. If the permanent expansion is there, there is a plastic limit, and here the elastic limit, it will regain its original position. The temporary change in the length will be taking place. Where E is the modulus of elasticity, S is the stress, epsilon is the strain, A is the cross sectional area. Then we can write for this work done in stretching a wire. F is equal to F the force is equal to stress into area, where this stress can be written as E into epsilon, because since modulus of elasticity is can be given by stress to strain, then stress can be written as E into this strain epsilon. Then that if you substitute in this one, S equal to E into epsilon, and this becomes the F will becomes a E into epsilon into A. Then change in stress is given by change in length to the original length. Then dw work done, that is a minus f dl, and dl can be substituted from this equation. Okay, dl will be L into d, this one, and f is substituted from this equation, E into epsilon into A, and this dl is L into d epsilon. Then total work done W can be written as minus A into epsilon into L 1 to 2 E in epsilon into E d epsilon. Then this can be written as A E L by 2 epsilon 1 square minus of epsilon 2 square. Okay, after the integration we are going to get this one. Work done in changing the area of a surface film. When the surface of the film changes its area, then there is a work done. And how that is work done is taken. And that is due to the surface tension. Okay, that we'll discuss here. A film on the surface of liquid has a surface tension. Film on the surface of the water has the surface tension. There is a tensile force acting on the surface of the fluid, which is a property of the liquid. Already this property we have discussed. And the surroundings. This is the property of the liquid and the surroundings. The surface tension acts to make the surface area of the liquid a minimum. It has the unit of force per unit length. The work done on homogeneous liquid film in changing its surface area by an infinitesimal amount dA is given by a very small amount of work done, that is dW is equal to minus sigma into dE, where sigma is the surface tension, that is in terms of the Newton per meter, and work done is equal to integration of this one 1 to 2 minus sigma into dA. The last one, magnetization of paramagnetic field. In the paramagnetic field, magnetization, if we get, it will be get magnetized, then there is a work done, and that how that can be taken. The work done per unit volume on magnetic material through which the magnetic and magnetization fields are uniform is dW is equal to minus h into dA, and W122 is equal to minus 1 to 2 h dA. Here h is the field strength of that paramagnetic field, and I is the component of the magnetization field in the direction of the field. The minus sign provides that an increase in magnetization, positive dI, involves negative work. Okay, the positive dI will be of the negative work, the work will be done on the system. Okay, then these are the different types of the other work transfers, and their equations are consolidated here. The following equations summarize the different forms of work transfer. The first one is the displacement work or compressible fluid. This can be taken as a flow work, that can be given as 1 to 2 PdV. Electrical work W is equal to 1 to 2 EDC as 1 to 2 EIDT. Ditto. Shaft work W is equal to 1 to 2 E d theta, and surface film W is equal to minus 1 to 2 sigma dA. Stretched wire W is equal to minus 1 to 2 F dl. Magnetization, magnetized solid W is equal to minus 1 to 2 HDI. These are the different other types of the heat transfer we are going to consider in the energy transfer. Thanks for watching. If you like, share, subscribe and comment.